Hello, my amazing students. Now this is when I really get desperate. I am in my car and I have my little whiteboard and I have your first problem of 1.2 here, and I figure as mobile as I am, I'm never at home, I might as well learn how to do this in my car so that you get the help that you need. So this is number 10 of 1.2. Our second video, and we're talking about domains here. So this is a problem I got out of the book. A set of people in a town is the domain. A doctor that any person uses is the correspondence between the domain and the range. Okay, and then a set of doctors is the range. And then they're saying, is this a function? Okay, does each person use only one doctor? Well, perhaps some people might use only one doctor, but as you age, you might have several different doctors that you have to see for different conditions. And so one person in town may use a heart doctor and a general physician and a surgeon. So all three of those are doctors and different doctors. So no, this is not a function because 1x, one input, has more than one output. One person may have more than one doctor. And I will be back with the next one. Okay, so here for problem number 20 on 1.2, we have just a set of ordered pairs, and I ran out of room, so the fifth one is over here. But we're trying to determine, is it a function? And what would you say? Okay, because I have a repeated 5. I've got 5 as an x that has 2 different outputs, and 3 as an input that has 2 different outputs. So I hope you can see this board in the slide here. Okay, so this is not a function. So not a function, but let's go ahead, and it is a relation. So relations can have domains and ranges too. So let's do the domain of the relation. So the domain is going to be a set that includes, I'm going to do them left to right, so 0 and 3 and 5. Okay, so there's only 3 elements in the domain because we do not repeat those. And then the range has got, looks like it's got maybe only 3 items too. Okay, because we have a -2, a -1, and a 0 in the range. So -2, -1, and 0 in the range because we had repeated ones of those also. All right, so on problem 30 in 1.2, we have been given a very hefty h of x. So this is a quartic because its lead term is x to the 4th, and so it's got a lot of terms that we're going to have to plug into, but we're supposed to find h of -11 and h of 7 and h of 15. Okay, so because I don't have my calculator out right now, I'm going to just plug this in. So we got 3 times -11 to the 4th, okay, and then minus 10 times -11 to the 3rd, and then plus 5 times -11 squared minus a -11 plus 6. Okay, so all of those things. Now, I'm going to get a calculator for these, but with this one, am I going to need to keep the negative in there? Because I've got a negative raised to the 4th power. So this one's going to wind up being positive, isn't it? This one, however, is going to keep its negative sign because it's raised to the 3rd power. And then this one, because it's raised to the 2nd power, is going to lose its negative. And then this one is a minus a negative and a positive 6. So I will get my calculator out and finish that one for you. But right now I have to go to class. So I went to class and I came back and I got my calculator out. And this one is going to be a positive answer because the 11 to the 4th squares out. And so I get that big number. And then I did the second one, which was negative 11 to the 3rd, which retained its negative. But then when I multiplied it by negative 10, I ended up getting 13,310. And then negative 11 squared is 121 times 5 is 605. And then a negative 11 is a positive 11. And then a positive 6. So that's what I got there. And then I added them all together and I got 57,855. So that was this one up here. That was h to the of a negative 11 when you plug in the negative 11 into this huge equation. So I'm not going to do the rest of those because they're all going to be just like that, where you take out the variable and you plug back in the number and do a lot of calculating. So I'm not going to do any more of those. I'm not going to do these other 3, but you have an example of how to do the one. So we will move on to problem number 40. Well, problem number 40 is a little problematic because it is a picture that we have to evaluate. So here is the picture of a parabola on problem number 40. And they're asking us to find g of negative 4. So what we're going to do is find where the x is negative 4. And x is going to be negative 4 right there at that point, negative 4. And it says negative 4 3/2. So the answer to the first one is going to be 3/2. And then they say g of negative 1. These are all g's. And g of negative 1 looks like it will be negative 3 because down at the very bottom of the parabola, you see a negative 1, negative 3. Okay, and then g of 0 is going to be negative 5/2 because they have that point labeled. You see negative 5/2 next to the 0. 0, negative 5/2. So that's just kind of one that's hard to show you because it's in the book and I can't write it on my board. So number 50 is kind of hard too. If you look at number 50 right here, it's a squiggle line that goes up, and we're trying to determine, is that a function or is that not a function? And that is not a function because the vertical line test would break it. So when you're looking at these, you go, okay, is this a function? Yeah, that's a function. That's a function, all right, because it's a parabola facing upward. This one right here is a function because it never crosses the vertical line twice. It's got a hole on one side and a solid point. So you can see that better in your book. That's 48. 47 right over here is called a step function. And it's got holes on one side and solid points on the other. So it is a function. Then 50 is not, and 49 is right here. And that one is definitely not a function. Okay, so remember the vertical line test on those. And now 60, I already did in one of my classes, but I'm going to put it on the video on a board. So back with 60 in a moment. Okay, so this is problem number 60, and this is actually a cube right there. That doesn't look like a cube, but that's a cube. And so we're trying to determine what the domain of this function is. And the domain is only going to be limited here by the denominator. The numerator can be whatever it needs to be. The denominator cannot go to 0. So the domain is influenced by that x, which if the x was 0, your function would be undefined. Therefore, we say, well, x cannot be 0. But to write that correctly in interval notation, we would say negative infinity to 0, union 0 to positive infinity. And that would be how we would write that domain in interval notation. And then in set notation, we would say the set of all x such that x is an element of the real, but x cannot be 0. So there's your set notation and your interval notation there for that problem. And I'm going to do another one of these, even though it's not a multiple of 10, because I just want you to be clear on this. Okay, we're going to talk about these two functions. One is a cubic root function that was actually in the textbook, and this one was just one I made that's like this one, but it's a square root function. The reason this is important, if you're finding your domain, is that when you have a cubed root looks like this. Okay, and a cubed root goes on and on forever, because a cubed root, remember, the cubed root of a -8 exists. The cubed root of a -8 is a -2. So underneath a cubed root, I can have positive or negative signs under the radical, and they're still real numbers. So this one exists for all x. Therefore, this one is going to be all real numbers in its domain. So this one is all real. But I want you to look at this one. Remember that square root functions go off in one direction, usually like this, okay? But since this is a -x right there, it's going to end up going off in the other direction, because if I were to move over to 4, all right, which is where this thing starts, because it goes to 0 at 4, if I plug in a 4. But if I plugged in a 5, which would be what we would normally think if we go off to the right, then I get 4 take away 5, which is negative, which means that this is not a real number. So, but if I plug in a 3, I'm okay. So the graph of this one would be 1, 2, 3, 4, because when I plug in a 4, I get a 0. If I plug in a, let's see, if I plug in a 5, it goes unreal. If I plug in a 3, then I'm going, a 3, then I'm going to get 4 minus 3 is 1. And the square root of 1 is 1. So it's going to go here. If I plug in a 0, then I'm going to get 4. And the square root of 4 is 2. So my square root sign is going this way to the left. Okay, so that's going to wind up being a -infinity to 4, including the 4, but never including the infinity. So that would be the domain. What about the range of this function? The range is limited as well, isn't it? Because there's nothing down here. So the range of this function would be from 0 to positive infinity. All right, so we'll come back with more. Okay, for 70, we have another graph. So I'm going to zoom in on 70 right here in the book. Okay, so the 70 right here is a little squiggle that goes up, and you're just finding the domain and the range for that. And if you look carefully, you can see the teacher's notes over here. The domain is -1 to 7. I'm -2 to 1. And the range is -4 to 4. And they've included both of those in brackets because they look to be included in the graph. So you're basically going to take, when you're doing the domain of a picture like that, you're going to be taking the leftmost point and the rightmost point will be your domain in between those, and the lowest point and the highest point will be your range. And that's all there is to those. So hopefully you've practiced some of those. So now we're going to go and do an 80. And 80 is pretty easy. It is one of our reciprocal functions. So an 80, put 80 on the board here. it says f of x is equal to 1 over x plus 1. And we're supposed to find our, we're supposed to graph it with the graphing calculator and then visually estimate the domain and the range. So here, what should be the domain of this function? Now we know that a reciprocal function like this, remember there's just an x in the bottom, there's no x on the top. It's going to look something like this. Remember that function that we've discussed? Okay, but it's not going to have a 0 on the y asymptote. That's not going to be it's going to move over. The vertical asymptote is going to be where? What can x not be? X cannot be -1. Okay, x cannot be -1 because when I plug in a -1, I get a 0, and that won't work. So this is the only thing that is eliminated from my domain. Now, what about the y-axis? Remember this one, this graph of this function has a no-go zone, an asymptote, all the way across horizontally on the x-axis. Now, that means that f of x can never be 0. Can f of x ever be 0? Here? Is there any number we can put down here for x that's ever going to make this become 0? And it's not. So we're going to have y cannot be 0 either. Okay, so x cannot be -1 because this one has been slid over, but because this function is actually this function just slid over to the left one, it's still got the y cannot be equal to 0. So that's going to be your domain, but we're going to graph it on the graphing calculator. The domain would be written as what? For the domain, we would say -infinity to -1 union -1 to infinity. Okay, so that's going to be your domain, and your range would be the same thing except it's going to have y. So we would say domain. Remember, your interval notation does not have variables in it. So for our range, we would just do the same thing, but we would leave out the 0. But let's do the same one on the graphing calculator. So I have my graphing calculator right here. And we're going to graph. So we're going to go on a graphing calculator, and I'm trying to get the light here because I'm in my car office. All right, so we're going to turn on the graphing calculator, and I'm going to go to my y equals button, and I need to clear out something here. So I'm going to clear out and clear and enter to where I have a nice clean y equals screen. And so now I'm doing, remember, 1 over x plus 1. So when I'm going to enter it in, I'm going to enter 1 divided by, so I'm going to hit my divided by, and then I want x plus 1 to stay on the denominator. So I'm going to put a parenthesis, and then I'm going to put an x plus 1 on the bottom, parenthesis. Okay, so now when I finish, it looks like that. 1 divided by parenthesis x plus 1. That keeps the denominator all together so that my calculator knows what I want. So now I'm going to hit the graph button and see what it graphs for me. Okay, now it's hard to see this, but it is this same shape here, isn't it? All right, look for that same shape. You can see, because my calculator, so you can see it's coming. The y is only going up to this x equals 0 line, the y equals 0 line here, the x-axis. So it's stopping there. So that's showing your y cannot be 0. But your x is slid over to where x cannot be the -1, right? That's going to the negative direction. I sure hope it's showing up negative on yours as well. Okay, so hopefully my screen is not flipping on the camera. We'll see how that turns out. But that's supposed to look like x cannot be -1. So hopefully it looks like -1 to you and not +1. But hopefully. All right, so That's how you're going to use your calculator to graph those. And I will be back with number 90, which I think is the last one for this one. Okay, so I came across one more problem that I wanted to do for you before we do number 90. And this is right above that. I'm not sure which number this one is, but it's just another square root that was in your problem set. So basically, because it's a square root, we know it's going to be a one-armed function. It's going to go off in one direction. And we're supposed to graph this and then tell whether it's what its domain is. So because a negative x is going to make this go to 0, we're going to come over here, negative 8. Did I say negative x? 1, 2, 3, 4, 5, 6, 7, 8. So negative 8 will make that go to 0. Now, if I go to negative 9, then this becomes negative. And when the radicand becomes negative, then I have not a real number. So I'm going to end up going this direction to the right. So let's plug in a negative 7. If we plug in a negative 7 plus an 8, we're going to get a 1 under here, and the square root of 1 is 1. So that's going to be there. And then if I plug in a negative 4, then this becomes a 4. Okay, it's negative 4. This whole thing becomes a 4. The square root of 4 is 2. So 1, 2, 3, 4, and up 2. So those are easy points to graph, right? So this is going to go off down that direction. So once you graph it, then you can see that it is going to be a negative 8 with a bracket to a positive infinity with a paren. So that would be your domain. But they wanted you to graph those on the graphing calculator. So here's my graphing calculator. And I'm going to clear out the old one. And now I'm going to, so I'm nice and clear, I'm going to use my square root function, which is a blue button down here on my x squared. So second, and then the square root, we'll put that there so I can see that everything after that, notice it already puts a little parenthesis, and I want x plus 8 in the parentheses. So x plus 8 parenthesis is the way I'm going to write it there. Okay, so I've got it all under the parenthesis, but the parenthesis doesn't really go over the whole thing. It's just kind of in front. But because you've got that paren, it's going to graph it. So I'm going to hit the graph button, and you can see that it's going off to the right from a negative 8. That's what it should look like. Okay, so now I want to do this other problem, which is number 90, the last one that we're going to do in this set before we go to 1.3. So the equation is horrendous. This was a word problem, and it's talking about the population of the United States in 1960, and they gave you the equation. So we didn't have to have all of that other stuff. Now you should be able to come up with the equation, but we didn't have to in this one. So they gave you the equation. It was so big with such big numbers that there's the rest of it down there. So big number, x plus big number. Okay, so that's what the population of the U.S. is. And the years are going after 1950. So basically in this problem, 1950 is our 0 year. Okay, so they want us to model what would the population be in 1980. Well, if 1950 is our 0 year, then 1980 would be our 30 year. Okay, so we're going to model 1980 with a year 30, and we're going to model 2020 with a year what? So from 50 plus 20 is year 70, and we're going to plug those into the equation. So we're going to plug in 30 in for the x, and this is definitely one you would want to have your calculator for, right? There's a 30 going into the x, and then we're going to multiply 30 times that, and we're going to add that big number to it, and we will get our population in 1980. And they said the population in 1980 was 226,474,709. I'm not going to do that math. Okay. Excuse me. So for 2020, we're going to use the year 70. So we're going to plug 70 right up here for the X, because it's the 70th year after 1950. Okay, so we're going to plug in the 70, and we're going to get, for that one, they said it was 326,916,309. A lot of people. Okay. And then lastly, it says, when will the population be approximately 400 million? Okay, so then when would the population be 400 million? So what are we going to do to solve that one? Is we're going to put the 400 million here in place of the P of X. And then we're going to find the X that goes with it. Okay, so we would put the 400 million here. We would subtract this one from it to get it on the other side. We would divide both sides by that really big number on our calculator, and we would get X. And the answer to that one is about 99 years. So approximately 99 years after 1950, because that's the starting point of the problem. So we would have to add the 99 years to the 1950, which would be 2049. So I just wanted to talk you through one of those. So there's the board that I have right now. Okay, and that is all of 1.2. And maybe for 1.3, I can find a place besides my car to talk to you in. But this is what I've got right now. So this is Mrs. A, and I hope that you have a wonderful, wonderful day.